Hello, my name is Daniel Angulo Jimenez, and today I'll be presenting my proposed idea in artificial blood vessels. For this research, the specific parameters of a portal vein will be used to analyze the results. The portal vein is a blood vessel that it delivers blood to the liver from the stomach, intestines, and pancreas. The portal vein supplies approximately 75% of blood flow to the liver. This vein has a diameter of about 5 millimeters and a wall thickness of 0.5 millimeters in normal adults. The mean volume flow rate of blood in the portal vein of a male adult when standing is 169 milliliters per minute. The environmental pressure inside a human body was found to be 0.0133 megapascals. The three different materials that we'll be analyzing in this experiment are EPTFE, Dacron, and polyurethane. EPTFE has a modulus of elasticity of 2.25 gigapascals, a yield strength of 41.4 megapascals, a density of 3,360 kilograms per meter cube, and a cost to manufacture this and a cost for this material is $9,500 per metric ton. Dacron has a modulus of elasticity of 5.2 gigapascals, a yield strength of 90 megapascals, and a density of 1,450 kilograms per meter cube. The cost to manufacture this material is $1,025 per metric ton. And lastly, polyurethane has a modulus of elasticity of 0.248 gigapascals, a yield strength of 34.5 megapascals, and a density of 1,400 kilograms per meter cube, and a cost of $4,070 per metric ton. In order to determine the best possible material, three sizes of vessels needed to be created. The first one had a length of 1 millimeter, the second one of 10 millimeters, and a third one of 100 millimeters. This is to make sure that the chosen material can work for a vessel replacement of any size. For each length, the three models were created, one for each material mentioned as before. As you can see in the drawing, the model matched the diameter dimensions of the portal vein with an inner diameter of 5 millimeters and an outer diameter of 5.5 millimeters. The flow simulation for each material for each length was conducted. The flow rate of 169 milliliters per minute was inputted as 2.8 times 10 to the negative 6 meter cube per second. For the second run of the simulations, a worst-case scenario test was conducted in order to analyze the response of the vessel in a flow rate that is 5 times larger than the common blood flow. This flow rate was determined to be 1.4 times 10 to the negative 5 meter cubes per second. The environmental pressure inside a human body was inputted as 0.0133 megapascals, as you guys can see in the SolidWorks screenshots. The maximum pressure for each material and for each length was recorded. The results showed that the material had little to no effect on the pressure experienced inside the vessel. The 1 millimeter showed results in the 0.103 megapascal range, the 10 millimeter showed results in the 0.1014 megapascals, and the 100 millimeter showed results in the 0.1015 megapascals. They're actually relatively close to each other. There is not much difference. The hoop stress is the stress that occurs along the vessel circumference when pressure is applied. Hoop stress are tensile and generated to resist the bursting effect that results from the application of pressure. Hoop stress is a function of the vessel's radius, the inner pressure, and a wall thickness. The equation, as you guys can see on the screen, is hoop stress is equal to pressure times the inner radius over the wall thickness, where T is the T is the wall thickness, R is the radius, and P is the pressure. As you can be seen in the results, an increase in pressure resulted in an increase in the stress the inner face of the vessel was experiencing. The hoop stress for every material stayed in the half megapascal range. There wasn't many variation, as there wasn't many variation in the pressure as well. The hoop stress determined earlier was used as an input load in the static simulations for determining the strain values. Strain is a ratio between the deflection of a material against its original dimensions. As it can be seen in the results, the models did not experience a significant deflection. From the results, the key findings were that all three materials are suitable for an artificial blood vessel. The stress generated due to the pressure inside the vessel is insignificant when compared to the mechanical properties for each material. The tensile strength of the materials are significantly greater than the hoop stress experienced by any of the three vessel sizes. Even in the worst case scenario, in which the flow rate was increased 5 times, the hoop stress stays below 1 megapascal. As it can be seen in the results, the model did not experience a significant deflection. All the materials being analyzed will be able to support the stresses generated by the blood flow. Therefore, the material recommendation will purely rely on the cost it will take to manufacture the vessel with the respective material. The material that costs the least is Dacron, with a price of $1,025 per metric ton. This material has a tensile strength of 90 megapascals, which is more than sufficient to condense the 0.507 megapascals that a pressure due to the human blood will generate. So this will be my recommendation, Dacron. And these are my references, and this is all for my presentation. Thank you so much.